So last day we ended our discussion on artificial neural network over here. Just before we proceed further, let's have a very small recap. What we have learned, that we started learning artificial neural network and we started with single layer perceptron. Single layer perceptron mean that we will have only one layer in between input and output layer. That's why single layer. Now we already also have uh, just a very small example of how the learning is happening. Learning in the sense changes of the weights associated with each and every connections between two neuron with input and output layer. And then we have an example here how we can implement AND function. I mean, not how, whether we can implement AND function or function or XOR function using singular perceptron or not. So what we have seen, that in case of and OR function, the the output, that is f, in form of zeros and ones, if you put them on a plot, you can easily see that you can draw a straight line boundary in between two different classes. One class from 0, one class from 1. In both cases, and OR. But if you go for XOR function, the 1 and 0 is placed in such a tricky situation that you cannot make a classification linear boundary to make 100% accurate classification. So here linear boundary is not possible, and here we concluded that linear separable line is not possible here. So if the linear separable line is not possible, then we cannot apply or we cannot go for single layer perceptron. So what was our solution? We have seen the solution. We have just came to know that the solution is Cover's theorem. So today we will start with what Cover's theorem is, and then we will try to understand how basically we are modifying our single layer perceptron to implement the Cover's theorem within it. So let's start. Lot of sentences here. I'll read all the sentences slowly and try, make it's easy to understand. So first thing is that it's a very small, uh, you know, uh, 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 you can say information about Converse theorem is given. That is a complex pattern classification problem. Cust is a high dimensional space of nonlinearity, is a more likely to be linear separable than in a low dimensional space, provided the space is non-densely populated. This particular definition is very difficult to understand, I know that. So don't try to understand Cover's theorem by this definition only. But one thing, just keep in mind what is writing, that casting means putting something, you know what casting means, right? So casting in a high dimensional space non-linearly is more likely to be linearly separable. That means if you have a set of data which is not linearly separable in some n dimensional space, there is a high probability to make it linearly separable in higher dimensional space, that is more than n dimension. Again, I'm just telling in a small line, I know, in a different way, but what exactly it is doing, let's see. So let's take an example. Like, let x denotes a set of n patterns. N patterns means n vectors, means in different points, you can say. Like, already I have seen a lot of points on the on a plot, right? Those points are representing a element in the data set. So same thing here. So x is a set of n points which is represented by x1, x2, x3 till xn. This x1 to xn will be from any one of the classes. Maybe x1 can be of class c1, x2 can be of class c2, x3 can be class of c1 again, something like that. So that is what written here, that each of which is assigned to one of the two classes c1 and c2. So among these n points, some of the points are from class c1 and some of the points are from class c2. Okay, it's a binary classification situation. So the dichotomy of the pattern is separable if there exists a surface that separates the pattern in class C1 from those class C2. And this is all we know, that we can say that the patterns is separable if there is exist a surface. So now question is that suppose this surface is not linearly, you cannot linearly separate the classes C1 and C2. That means those set of points from C1 with another set of points from C2 among this X set. I mean within this X set. Okay. How to do this? Let's see. Just, I'm just reading and trying to make it easier to understand. So let's see one by one what I've written, that for each pattern x, small x, you see, small x belongs to capital X, means this small x is just a representation of a element of this set X. That means this small x can be x1, can be x2, can be x3, anyone till xn. Okay. So for each pattern X belongs to capital X, define a vector made up of a set of real valued function, something like this. What does it mean? You see, just try to understand that I'm saying that a vector made up of a real valued function. So that means the element of the vector is not a value. The element of the vector is basically some function. I'm telling you again. Let's take a vector. Vector say x1, x2, x3, x4. It's a vector. So what is x1, x2, x3, x4? Some value. Generally, what we know that, right? But here I am saying that I'm creating a vector where each and every element is different functions, which is represented by phi ix. Okay, this I can be 1 to m1. You see, point to be noted here. I have kept the the dimension of this I is as m1, not n. N is the total number of element in the data set X, capital X, the total number of element, including class 1 and class 2. That is not related with this, remember. Anyway, so how the vector will look like? The vector will look like phi x, like this. I told you that I'm creating a vector where each and every element will be function. So same thing like this. Phi x equal to phi ix, I mean phi 1x, phi 2x, dot 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 phi m1x, because I started from 1 to m1. So it's a vector. Simple. Fine. Now assume that this x is a vector which is in a m0 dimensional input space. What does it mean? It means that this x, which is one element of capital X set. So this x means maybe x1, maybe x2. I mean this one, what I'm trying to say. This one. x1 or maybe x2 or maybe x3 or maybe xn, whatever. One of these, a representation as simple x. So this x is a vector of m0 dimensional input space. That means this small x is a vector again, which has m0 element. Okay, so you can say something like x1 is a form of say some set of values. Similarly, x2 will be some vector of some similar number of values. X3 will be another vector of similar number of same number of values. All these x1, x2, x3 are from the set A, capital X. Okay. So don't get confused. There are three things we have seen. Again, I'm telling you, capital X is the total set. How many elements are there in this set? Total capital N elements is there. Each and every element of the X set I'm representing as x1, x2 till xn. Fine. Now, what is the dimension of x1? M0. What is the dimension of x2? M0. What is the dimension of x3? M0 till xn. Why I am saying this? Because I have written here this small x, which is a, you can say, a representative of x1, x2 till xn, which is belongs to capital X. That's why. So m0 is the dimension of a single element of set capital X. And here I have created a vector of real valued function, and that vector dimension is m1. Okay. Now what I am doing, I'm saying that in this m0 dimension input space, so that means x1, x2 till xn, that means all the points in this capital X set, which is some of them which are from C1 class and some of them which are from C2 class, are not are all have m0 dimension, and we are assume that these points x1 to xn are not linearly separable in m0 dimensional input space. Okay, so let's come to the third point. What is written? The vector phi x, this one, maps the point in m0 dimensional input space into corresponding points in a new space of dimension m1. So this phi x is basically a mapping vector, which is mapping a vector of m0 dimension space to m1 dimension. How it is mapping? It is mapping because each and every element of the, say, x1, I mean this x1 is of m0 dimension space. I am mapping the x1 of m0 dimension space to corresponding m1 dimension with the help of phi x. How? Why? Because the number of elements present in phi x is m1. Okay. We refer to phi ix as hidden function, and the set hidden function looks something like this, is referred to as feature space. So that means what exactly phi x is doing? We can say that phi x is the nonlinear transformation from m0 to m1 dimension space. If you see the right hand side here, I hope a bit clear to you what's happening. You see, this xi is what? Xi means I can be 1, can be 2, can be 3, can be capital N. Right? Any element of set capital X. So what I am doing, I am passing that particular xi element with m0 dimension to this function. The same element I am also passing with this function. The same element I am also passing with phi 3x function. Till the same m0 vector xi I am passing to phi m1 function. So what will happen? Naturally, there will be some calculation in between this function, this function definition and the vector, right, which will produce some output here. Again, some calculation will happen in between m0 dimension vector of xi with this function and will produce some output. In this way, till the last box, some calculation will happen between m0 dimension vectors of xi with this function and get some output. So total how many output I will get? I will total get m1 number of output. Why? Because I have total m1 number of boxes, right? So in the right hand side, what basically you are getting? You are getting another vector having m1 number of element within the vector. In the input, what you had? You had a vector having m0 number of element. So in the input, I have xi with m0 dimension. In the output, after transforming through this phi ix, phi 2x till phi mx, m1x, I am getting same xi but with m1 dimension. So what basically that mean doing? What that mean this phi x is doing? It is, you can say, it is non-linearly transforming the any pattern or any data of m0 dimension to m1 dimension. So this is what the Kovar's theorem is. Now let's just gist up what actually you have done. That to sum up, Kovar's theorem on the separability of patterns encompass two basic ingredients. One, nonlinear formulation of the hidden function, what we have just seen, and another is that high dimensionality of the hidden or what we call feature space compared with the input space, whether the dimensionality of the hidden space is determined by the value assigned by m1. So that means with respect to a simple machine learning, data processing part, you can say that this xi is nothing but an input data that you have in your hand, right? And assume that you can see that you have, in this way you have a lot of points. I mean, I is just a, I can be anything, I can be 1 to n anything, right? So just assume instead of I it is 1 or maybe 2 or maybe 3. I mean, for all i's, just you consider it's not linearly separable. So what you can do, you can transform that lower dimension space to higher dimension, and what will be the higher dimension value, that is the value of m1, that you can decide. Say for example, m0 may be 3, that means 3 features are there in your data set. Okay, each and every point is represented by 3 features. That means the value of m0 is 3, right? Now assume that you can see that with these 3 features means total 3 dimension, right? So now in a 3 dimension space, the points that are presented are not linearly separable. What you can do, you can map those 3 dimensional space to say 10 dimensional space. For example, 10. What does it mean? It means that each and every point which was now represented by 3 features will be now represented by 10 features. So how these 7 features has been added? That has been added with the help of that non-linear transformation function, which is nothing but this phi yx, phi 1x or phi 2x till phi m1x. So if you want to get 10 dimension feature from that 3 dimension feature point, you have to have 10 phi functions. So phi I, phi 1, phi 2, in this way value of m1 should be 10, so that in the output you will get total 10 outputs, and that means each and every point of 3 features will be represented by the point of 10 features. Just assume like this. So that is what actually written here. Now question is that what will be the nonlinear function definition? What will be the definition of phi ix? Right. So we will see that soon. But before that, just try to understand with respect to a visual interpretation is like that. You have an input space is something like this. It's a 2D. You can easily see that in 2D it is not linearly separable. You have to have some, some curve. But I want to make it linearly separable. I want to make a plane in between two different data set, or maybe straight line, or maybe a hyperplane. Right. So what we can do? We can do the transformation from 2 dimension to 3 dimension, for example. So here m0 value is 2 and here m1 value will be 3. Once you change the dimension, automatically you will see, because of the third dimension added in the dataset, the points will be something like this, in this form, so that you can create a hyperplane in between them and they become non-linearly separable. And you see that number of features are called, that particular dimension is called feature space. So we have an input space is this 2 and feature space is 3. Why I am saying feature space? Because in this space the data sets are linearly separable. So this is all about the Cover's theorem. Now question is that how we are applying this Cover's theorem in our singular perceptron, so that the problem of non-linearly separable patterns can be solved. So let's see. That we will come now with a new form of artificial neural network which we call multi-layer perceptron. We had single layer, now we'll have multi-layer perceptron. Let's see what multi-layer perceptron is.